Okay, in this video we're going to talk about circular motion and how that kind of changes the way we've done some things in the past. Okay, so we've talked about moving in a straight line. Now what we want to do is introduce this new idea. So for circular motion, okay, the idea is kind of simple. Let's pretend that you have an object that's moving in a circular path. Okay, and so this object could be anything. And the circular path has a radius r to it. All right, and we'll give it some meaning. So let's say the object is a baseball. Now, at any moment in time, it's important to understand that this ball is trying to move in a straight line. If this was a ball attached to a rope and you were to let go of the rope, the ball would go off into a straight line, and that's important. There's conceptual questions that ask, like maybe the ball continues to curve, or maybe it curves off the circle. But in reality, if you let go of that rope, it'll fly off in a straight line. So it's true that no matter where it is in the path, it'll always be moving at a straight line. Okay? Now, the only exception to this, and I probably didn't draw it perfectly right, but if this was moving at constant speed, then what is causing the vector of the velocity to change direction? Okay, so how do you change the direction of velocity without changing the magnitude or the speed? Okay, so if you think about it, if I have an acceleration that's in the same direction as the velocity, that will change the speed. But if I have an acceleration that's perpendicular to the velocity, then that will not change the speed at all, but it will change the direction. So it turns out that at every single point, there's an acceleration that's at a right angle towards the center of the circle. Okay? So every one of these accelerations is pointing towards the center of the circle, and they should be roughly or exactly 90 degrees to the velocity vector. And that'll just change the direction, but not the magnitude. Okay, and so the acceleration that points towards the center, we call that a centripetal acceleration. And it's labeled with it's just an acceleration A labeled with a C for centripetal. Okay, and the reason it's called this is because centripetal is a fancy way of saying center seeking. So when we say a centripetal acceleration, we're referring to an acceleration that's pointing towards or seeking the center. Same thing for a centripetal force. If we have a centripetal force, that's a force pointing towards the center. Okay? And if we did some quantitative analysis on something moving in a circle, we would find that the centripetal acceleration is equal to the velocity that's tangent to the curve squared divided by the radius of the circle. And that would tell us the centripetal acceleration of an object moving in a circle. Now, I mentioned that the speed was constant, and that's not always going to be the case. So let's look at an example of that. So to separate the two ideas of either moving at constant speed or not moving at constant speed, we refer to those things as either a uniform circular motion and non-uniform circular motion. Okay, where the term uniform represents constant speed and non-uniform represents us changing speed. Okay, so to recap, a constant speed circular motion or uniform circular motion would be an object that moves in a circle. Again, the velocity is always tangent to the curve. And at every one of these points, there's an acceleration that points towards the center. Again, our centripetal acceleration. Now, in non-uniform, you're still moving in a circular path. Your velocity is still tangent to the curve. But now, at different points, your velocity vector may change in length. So in other words, the speed or the magnitude of velocity is changing. So in order to stay in the circle, you still have to have a centripetal acceleration. But in order for the magnitude to change, you have to have an acceleration that's tangent to the curve as well. So at every single point, if you're in non-uniform circular motion, you have to consider a tangent acceleration as well. So then overall, we could say that there is a total acceleration vector, which represents the hypotenuse at every one of these points. And that hypotenuse is going to change both the direction and the speed of an object that's moving in a circle. And that would be how we do non-uniform circular motion. And so the main differences between the two is if it's uniform, it only has centripetal. But if it's non-uniform, then there's an overall acceleration vector whose magnitude is the vector sum, or Pythagorean theorem, of the centripetal acceleration squared and the tangent acceleration squared. Okay? And the formulas for these, which we already know, would be that the centripetal acceleration is v squared over r, and the tangent acceleration is a rate of change of the velocity with time. Okay. So let's go into some examples with this. So say we have an object moving in a circle. Okay, knowing the centripetal acceleration is good, but we need to do a little bit more than that. So in this example, we have a ball of mass m that's moving in a circle, and let's say the ball is attached to a string of length r. So r represents the length of this rope, which in effect makes the radius of the circle. At every point, the velocity is in a straight line, and we'll say that it's going in uniform circular motion. So there's only a centripetal acceleration towards the center. So we want to know, what is the tension in the rope? So let's start with a free body diagram. If we were looking at this from the side, so we'll say this is a horizontal circle, so I'm spinning it above my head and you're standing next to me watching the ball. At any given point, if you looked at the ball, you would see a gravity vector pointing straight down, but then you'd also have a tension vector pointing towards the center of the circle. Now, here is, first of all, there's a conceptual thing here. You'll never have a tension going straight across or straight on the x-axis if gravity is straight on the y-axis. And you have to think about that, because if you look at the diagram, there's nothing canceling gravity. So by Newton's first law, this thing should be falling. But it's not. And the reason why is because when you see it, the tension has a slight angle to it, which helps to cancel off the gravity effect. But we're not going to, we're oversimplifying the problem here to say that tension's straight over to the left. But just keep in mind that realistically, you can't have a horizontal tension because there has to be some upward component to cancel gravity. Okay, so since the tension vector is pointing towards the center, that makes our net force have to be a mass times an acceleration, and in this case centripetal. So let's review a little bit about net force. So we were used to doing equilibrium where the net force was either 0 because you're at rest, or it's 0 because you're moving with constant speed. We also did a net force that said you're moving, but we don't know exactly how. It doesn't necessarily have to be a constant speed, but you're moving, and which means all we can do then is Newton's second law, which is mass times acceleration. When you're moving in a circle, you have no choice. The net force has to be mass times the centripetal acceleration. Okay, so since the net force has to be mass times centripetal acceleration, the only force acting on the object is tension. And again, centripetal acceleration is v squared over r. So if we were going to solve for the tension, we would need these numbers, but effectively we see that the tension is equal to the mass times the velocity squared, the tangent velocity squared, divided by the radius. So with some numbers, we could figure out the tension in that rope. Now let's look at another example. So in this example, we're going to look at a car that's going around a curve. Okay, so it's important to understand again that this car, even though it is turning, at every instant the car is trying to go in a straight line. So there's got to be something holding it into the curve. So let's say that the road itself has a curvature of about 20 meters, and there's a friction coefficient on this car of 0.5. So we need to figure out the speed. Now notice, the coefficient here is a static coefficient because it's not, even though the car is moving, you have to focus on the tire's interaction with the road. The tire, as it turns, sticks to the road, and there's no sliding between the tire and the road. So once the car turns and the wheel rotates, that pulls the car forward. So there's no sliding between the tire and the road. Therefore, it's a static friction. Okay, if it was kinetic friction, you would be actually sliding off the road. So if we made a free body diagram for this car, we would see gravity pulling it down. We would see a normal force from the road. And then in order for the car not to slide off the road, there must be friction pointing towards the center of the circle in order to keep it in the circle. That makes the friction force our centripetal force. So when we set up our net forces for both the x and the y, in the x direction, all we have is friction, and that's going to equal mass times the centripetal acceleration. In the y direction, we have the normal force minus gravity, and since the car is not moving up and down, those must be canceling. So if we're trying to solve for the maximum velocity, we're going to need the frictional force. In order to get friction, we're going to need the normal force. So we can see from the y direction that normal force is simply equal to the gravitational pull. Now, notice also that we're at the maximum static friction because any faster than this will go beyond friction's capability and we will start to slide away from the circle. So if we're going at max speed, we're talking the maximum amount of static friction. Because any slower than this, we haven't reached max friction, and so friction will have an easy way of keeping us right where we are. So if friction's at max, that's coefficient times the normal. On the centripetal side, we have mass times v squared over r. Okay, we found that we know normal force is equal to gravity, mg. And so if we do some quick algebra steps here, we see that the m's will disappear. We multiply the r to both sides, and we find that the velocity is equal to the square root of the coefficient times gravity times r, which if we plug in numbers, coefficient was 0.5, we'll say gravity is right around 10, and the radius was 20 meters. So effectively then, the velocity has to be no bigger than 10 meters per second. Again, if the velocity is any bigger than this, we will slide away from the circle. Okay. Now, in order to make a turn without friction, it's not impossible. In fact, most racetracks are built that way. In order to reduce the friction so the cars can go faster, most of the time racetrack tires are bald. They don't have any treads on them. And so that you would think would cause a problem because if they try to turn and there's no treads, then there's no friction to help keep them in the turn. So what race car tracks do is they actually bank the roads. They make the roads slanted. So let's look at what a slant road will do. So same curved road, we'll do the exact same example, a 1,000-kilogram car moving in a straight line at every instant on a road with a 20-meter curvature. But this time the road is banked. So if we were looking at the car from behind the car, we would see as if the car is on a ramp. And let's just say that this ramp is 30 degrees. Okay, it would look like this to us if the road was banked. Okay, and we're going to say that there's no friction on this roadway. So now, same question, what is the maximum speed that we can have to stay inside this circle? So looking at like our picture of what looks like a ramp, let's go ahead and make our free body diagram. We have gravity straight down. We have a normal force slanted up to the left, and that's it. Now, if this was a ramp problem, we would have said that the ramp represents our x-axis. The problem is we can't do that now because towards the center of the circle is directly to the left. That means we want our x-axis to be directly to the left, which makes our y-axis straight vertical. So on a ramp problem, gravity was the vector we had to fix. But this isn't a ramp. This is a car moving in a circle. And so for that, the normal force is what is actually holding the car in the circle. You could see by the picture that the normal force has a component that's towards the center of the circle. And so that component is what's holding the car into the circle. Okay, so let's solve for that velocity. So with the angle where it is, we're going to have to fix the normal force vector. So let's start a new diagram. Gravity is still straight down. But now, vertically, we have normal force times the cosine of 30. And horizontally, we have the normal force times the sine of 30. So when we write out our net force equations, the net force in the x direction would simply be the normal force times the sine of 30. Now keep in mind, that direction is towards the center of the circle. That makes this net force centripetal. In the y direction, the forces are balanced. So the normal force, cosine 30, minus gravity, are balancing each other out, so that net force is 0. So in order for us to figure out v, which is in the x equation, we have to know the normal force. So we start by doing that in the y equation. So we simply add gravity to the other side, then divide away the cosine. Now, we could plug in numbers here, but you'll see that if we don't and we save the plugging in numbers till later, we might be able to reduce this algebraically down and make the calculation more accurate for ourselves. All right, so let's write out the net force in the x direction. And that's normal force sine 30 is equal to the mass times the centripetal acceleration, which is v squared over r. Now the expression for the normal force that we just got was mg cosine of 30 times the sine of 30 is equal to mv squared over r. So now if we do some algebra steps here, you'll see that the m's go away and we multiply both sides by r so that we've got gr on the left, and notice sine over cosine is actually the tangent of 30, and that's all equal to v squared. So take the square root of all that, and then we could figure out that the velocity has to be right around 10.7 meters per second. So again, if the car goes any faster than 10.7, it'll slide up the ramp or away from the circle. If it goes slower than this, it'll actually slide a little bit down the ramp. So 10.7 is the exact velocity needed to stay into that circle. All right, let's do another example. So we did cars on a flat road and on a bank road. We did an object tied to a string going in a circle. But let's look at something that's a little more like something you felt before. Okay, so let's imagine like a Ferris wheel. Now, as you're riding on the Ferris wheel, say the Ferris wheel has a radius of 10 meters. I don't know how accurate that is, but we'll go with it. As you're going around the Ferris wheel, you notice that as you go over the top, your stomach gets a little tickle in it. When you go around the bottom, you feel yourself press into the seat. And so we're going to talk a little bit about why that's happening. So as you're going around the top, the question would be something to the effect of, what is your apparent weight at the top of the roller coaster? We could ask the same question at the bottom. Now, notice that apparent weight, remember weight is an act of measuring something. And so what we're really looking for is the normal force of what would essentially be a scale reading if you were sitting on a scale. So let's start at the top, and let's assume that you have a mass of 70 kilograms, okay, and you're moving in such a way that we're going to define something different here. Okay, so there's a term in physics we use called the period. Period is the time it takes to complete one revolution. Okay, usually with a capital T. And so what we're going to say here is that maybe to go one time around the Ferris wheel, it takes 60 seconds. Okay, so we're not told how fast we're going, but we're told that it's going to take us 1 minute to go all the way around the Ferris wheel. Okay, so let's start with the top. So at the top, if we make a free body diagram, we have the weight pulling us down and the normal force pushing up. Now, what's important here is to identify which way is towards the center of the circle. So from this picture, towards the center should be downward because you're at the top of the Ferris wheel. That means our net force should be downward, and so for that reason we should consider the positive direction to be downward. That being the case, mg is actually positive and the normal force is negative. And again, it's towards the center, so this should be centripetal. Okay, so if we want to solve for the normal force, which again would be our scale reading, we're going to do mg minus mass times centripetal acceleration, which gives us our normal force. Remember, centripetal acceleration is v squared over r. Now, how do we find the velocity? Because all we're told is the period. Well, remember, if you're going at a constant speed, then velocity is simply your distance divided by your time. So if we're told the period, the time it takes to go 1 complete revolution, how much distance is covered in 1 period? Well, going around a circle, that would be the circumference of the circle. So what we're going to do is we're going to plug in that expression for v. 2 pi r over the period, the whole thing squared, divided by r. So when we do this, we get 2 squared is 4, pi squared, r squared over t squared, all divided by r. So one of those r's is going to cancel. And what we're left with is mass times 4 pi squared times r divided by the period squared. So when you crunch all these numbers, where the mass is 70 kilograms, gravity is about 10, r is 10 meters, and the period was 60 seconds, you find a normal force of about 692 newtons. Now, for comparison's sake, the force of gravity that acts on this object, if it was at rest, is mass times gravity, for a total of 70 kilograms at 10 meters per second squared. Again, assume gravity is about 10. So there's a resting weight of 700 newtons. But when you compare that to when you're at the top of the Ferris wheel, your weight actually went down a little bit. This is why, if you go over the top of the ride, you feel that tickle, because you actually lift off the seat just enough that you feel that motion. And so if you were sitting on a bathroom scale, for example, you would see the bathroom scale number drop because you are literally lifting off of it. Okay, now what if you were at the bottom of the Ferris wheel? So at the bottom, you still have gravity holding you down and a normal force pushing up on you. But what's different now is identifying which way is towards the center of the circle. And in this case, since we're at the bottom, towards the center would actually be upwards, which means our net force needs to be upwards. So the positive direction now is up. So normal force minus the gravity is equal to mv squared over r. So the normal force then is now the centripetal force, mv squared over r, plus gravity. Now we can use the same expression we found for v in the last problem. So after all the cancellations, it's going to be 4 pi squared r over t squared times m plus gravity. Again, plug in all the numbers, and you find a normal force of roughly 710 newtons. So again, comparing this to the original resting weight, you actually feel like you gain some weight when you reach the bottom. And the reason for this is, imagine if you're sitting in that cart. The cart's trying to go in a circle, but you are going in a straight line. So as you are moving straight, the cart is moving around, and you are actually impacting the seat. The seat is getting in your way. So you're hitting the seat with a little added impact force, which is what increases the effective weight.